Hey folks, welcome back again to Advent of Code in F#. Or at least that's where we're gonna resume, because it's been a couple of busy days for me. I have not been able to keep up with my puzzles, and instead of falling behind, I'm just gonna resume where we are. So I'm gonna pick up at day 15, and we're gonna pick up all those missing stars when things quiet down at work a bit. So let's take a look at what 15 has for us today. Lens library. The newly focused parabolic reflector dish is sending all of the collected light to a point on the side of yet another mountain, the largest mountain on Lava Island. As we approach the mountain, we find that the light is being collected by the wall of a large facility embedded in the mountainside. You find a door under a large sign that says Lava Production Facility, and next to a smaller sign that says Danger, personal protective equipment required beyond this point. As you step inside, you are immediately greeted by a somewhat panicked reindeer wearing goggles and a loose-fitting hard hat. The reindeer leads you to a shelf of goggles and hard hats. You quickly find some that fit, and then further into the facility. At one point, you pass a button with a faint snout mark and the label Push for Help. No wonder you were loaded into that trebuchet so quickly. That's day one. Cool. You pass through a final set of doors surrounded with even more warning signs and into what must be the room that collects all of the light from outside. As you admire the large assortment of lenses available to further focus the light, the reindeer brings you a book titled Initialization Manual. Hello, the book cheerfully begins, apparently unaware of the concerned reindeer reading over your shoulder. This procedure will let you bring the lava production facility online, all without burning or melting anything unintended. Before you begin, please be prepared to use the holiday ASCII string helper algorithm. You turn to Appendix 1A. The reindeer leans closer with interest. The hash algorithm, the holiday ASCII string helper algorithm, is a way to turn any string of characters into a single number in the range of 0 to 2 to 55. To run the hash algorithm on a string, start with the current value of 0, then for each character in the string, yada yada yada. So we determine ASCII codes, we increase the value of the hash by the ASCII code we determined. We multiply by some number, it's a prime. Set the current value to the remainder of dividing itself by, so it's a modulo. Okay. Or we're gonna have to do this a bunch of times, or today will be pretty straightforward. After following these steps for each character in the string order, the current value is the output of the hash algorithm. Okay, so a basic hash. To find the result of running the hash algorithm on the string hash itself, it's almost like we're entering Quine territory. The current value starts at something we find first, ASCII value multiplied by 70, modulo 256, yes, and we continue going on. And then we end up with a final hash value. Makes sense. The initialization sequence, our input is a comma-separated list. This looks like assembly, right? Are we getting into write your own assembly interpreter in the coming days? I think so, but not today. Today we're just calculating hashes. So initialization sequence is a comma-separated list of steps to start the facility. Ignore new line characters when parsing the initialization sequence. New line characters? Where are they at? I don't see any. Why are they stating that explicitly? No, I don't see any new lines. Don't know where this is coming from. To verify that your hash algorithm is working, the book offers the sum of the result of running the hash algorithm on each step in the sequence. For example, sequence, it specifies individual steps 11, so it's comma separated. Yes, we knew that. Result of running the hash algorithm on each of the steps. We just parse character by character and do the thing, makes sense. And then we have hashes for every step. We sum those up. That sounds very doable. Let's grab our example. I already grabbed my input, and if I saw correctly, yeah, it's just a single line, a comma separated list of steps, which is exactly what's in the example. We don't need to do a lot of parsing today. We're splitting on new lines. We can just ignore new lines, but I don't see any new lines. Not in our input, not in the example. So, okay, fine. I'm just gonna drop to read all text. I'm just gonna get rid of all this list things because we don't need any list stuff. We don't need to split. We just have strings here. Single line strings. Okay, let's continue. Let's work on the example, and let's first parse our example input into steps. There we go. Not that hard. Now for every step, is PC minus a correct instruction? Yeah. Oh, this is like registers, assigning, decrementing. No, we're looking ahead. This is for a problem for another day. Let's first try to hash. So we have our steps, and now for every step we have to calculate the hash. So it's a map. Let's make this a list instead of an array, because I don't know, I have a random preference for lists apparently. And now let's do a hash. Is hash an existing function? Yes. So let's make it our hash. So it's a function called hash step, which does not exist just yet. And there we go. So it's a step. Step is a string, but that's like a sequence of characters, and it returns a number between 0 and 255. An integer is more than enough. So compiler should be happy. Yes, compiler is happy. Okay, hashing. Hashing, starting with a value of 0 and then doing the thing, sounds like another fold. Fold to a rescue yet again. So let's fold. I'm gonna call my hash h, and I'm gonna call a character, because hash is a reserved keyword. Can I just put it in here? Actually, I can. So fold takes a state and the next element and returns a state. So it returns the hash, but it does something with it, and the initial hash value is 0, right? No, not correct. Oh, and we don't have to return -1 anymore. So yeah, this will return 0 for now, but now we can start to implement our hashing function right here. So I'm gonna extract that into a tiny little helper function, which takes the current hash value, the new value, or the new character value, and it returns the hash. So now everything is in place to start working on this hashing algorithm. The value starts at 0. That's what we provide as the initial state right here. So we don't need to do anything for that. Then we calculate ASCII value. ASCII value of uppercase H should be 72. Can we just cast that to an int? We can. Is that a fail-safe way? Let's assume it's a fail-safe way. So ASCII value character. Can I just do this? Yes, I can. So that's the ASCII value. We increase our current hash value. Yeah, so this is current value. Let's call that current value. to make it really clear. And we add the ASCII value and we multiply by 17. It was a prime, that much I remember. Yes, and then we do modulo 256. Let's make sure that works. So let's write a quick test, see if that works. Modulo 256. And that is the next value we need to take as current value, right? Then we do next thing, 265. 256 plus 65. Is that 265? No. Oh, sorry, it's 200. So it should be 200 if we just provide a H as an input to our hash. So let's test that. Let's do a hash step. And the step is just the H, and that should be 200, right? Why is there red squigglies all over the place? Okay, it was just a delay. Yeah, that works. So we have our hasher. It works for single H. Let's do a quick verification with the hash step. It should give us 52. Is that correct? Yeah, that's correct. So we can do it for the example, just to make sure. It gives us a list of hashes, and that sum should be somewhere in the problem description. 1320. 1320 looks good. And let's wrap that in a solve function, as we always do, and return the result, and have this function work on the input argument. And then we need to provide a type hint. There we go. So now we can solve for any kind of string. And in our test, let's wrap the example. I already forgot. There we go. 1320. Yeah, that works. Let's run it on our input. We have a biggish number. That's a gold star right there. So let's take a look at part 2. There we go. There we go. We can forget all about part 1 and continue on. You convince the reindeer to bring you the page. The page confirms that your hash algorithm is working. The book goes on to describe a series of 256 boxes, numbered 0 to 255. The boxes are arranged in a line starting from the point where light enters the facility. The boxes have holes that allow the light to pass from one box to the next all the way down the line. Okay. Inside each box there are several lens slots that will keep a lens correctly positioned to focus light passing through the box. Oh Jesus, this is a big part too. Okay. The side of each box has a panel that opens to allow you to insert or remove lenses as necessary. Along the wall running parallel to the boxes is a large library containing lenses organized by focal length ranging from 1 to 9. Reindeer also brings you a small handheld label printer. I have been using a lot of label printers at work, so I am having PTSD flashbacks right now. But okay, the book goes on to explain how to perform each step in the initialization sequence, a process it calls the holiday ASCII string helper manual arrangement procedure, or HASHMAP for short. You gotta give it to the writers this year. I'm a fan. Each step begins with a sequence of letters that indicate the label of the lens on which the step operates. I'm gonna need an example to parse that sentence. The result of running the hash algorithm on the label indicates the correct box for that step. Okay, it's a bit more involved, I see. The label will be immediately followed by a character that indicates the operation. Okay, we're not building a instruction set just now, we're just gonna do it today in part 2. It's not for future us, it's for right now us. So we have an equals sign or a dash operator. A dash means go to the relevant box and remove the lens with the given label if it's present in the box. Okay, then move any remaining lenses as far forward in the box as they can go without changing their order, filling any space made by removing the indicated lens. Okay, if the operation character is an equal sign, it will be followed by a number indicating the focal length of the lens that needs to go into the box. Be sure to use the label maker to mark the lens with the label given in the beginning of the step so you can find it later. There are two possible situations. If there's already a lens in the box with the same label, replace the old lens with the new lens. Remove the old lens and put the new lens in its place, not moving any other lenses in the box. Is it like HASHMAP a metaphor? Are we literally building a HASHMAP? We are literally building a HASHMAP. We have buckets that all point to a hash. And in these boxes we have like sequences and we're shoving things in, replacing them. We are literally working on a hash map here. Cool. If there is not already a lens in the box with the same label, add the lens to the box immediately behind any lenses. So it's behind, okay? Don't move any of the other lenses when you do this. If there aren't any lenses in the box, the new lens goes all the way to the front of the box. Yeah, makes sense. Here's the contents of every box after each step in the example initialization sequence above. So we have Rn equals 1. That means find how did we figure out the box? That's hashing Rn, right? So let's try that. Let's hash Rn. Zero. So yeah, that's box 0. So we hash the thingamajig on the left, and then we hash the operator, which meant equals meant adding it to that box. So we're adding 1 to box at 0, and the label maker we put on the label Rn. And then we try to remove CM in box, whichever CM hashes to, but it's not in there. So yeah, then we add a 3 in QP, which hashes to 1, makes sense. This hashes to 0 again. And we are removing QP. What was the minus thing again? Go to the relevant box and remove the lens with the given label. What do they mean, given label? Oh yeah, it's also the label. So this is remove QP from box QP. And there was a QP in box 1, which hashes to... Okay, yeah, it's starting to make sense. All boxes are always present. Only the boxes that contain any lenses are shown here. Within each box, lenses are listed from front to back. Each lens is shown as its label and focal length in square brackets. To confirm that all of the lenses are installed correctly, add up the focusing power of all of the lenses. So it's a simple calculation again to get a number out. And that's 1 plus the box number of the lens in question, slot number of the lens, focal length of the lens, box number, slot, focal length. Okay, box number is the hash. This is the index within the bucket, and that's the value of the lens's focal length. Okay, this sounds doable. A bit more involved. There were some edgy cases. These things, let's keep those in mind when we work on our solution. So we are building our own hash map. Should we use a hash map to represent our own custom hash map? What's the best data structure here? So we are mapping this to a box, and every box contains a list of potential lenses which are labeled with our label marker, and they all have focal lengths. So we could use a HASHMAP or an F# map with our box IDs or hash values as keys from 0 to 255, and a list of labeled lenses which know their focal length as values. So let's do some type-driven development and let's figure out some types. Yeah. Did I not save? Okay, I did save. Okay, so let's take a look at our types. I'm just gonna call it HASHMAP. Why not? And let's map of our hashes to a list of labeled lenses, something like this. Our hash is just a number, it's the 0 to 255. Our labeled lens is a label, it's a record containing a label, just a string, and a focal length, just an integer. And I think that's all the types we need. Now let's look at our abstract data, or let's look at the functions we need. What do we need to be able to do? We need to iterate over our steps. So we got our steps right here. Let's play around with the example again. And for every step we need to do something now. So again, that's a fold with our empty hash map. Yeah, sounds like another fold. We do it step by step. Yeah. So apply step is our folding function, and our empty state should be an empty hash map. So that's map empty. There we go. And our apply step function takes a map and a step, and it returns a new version of the hash map where we do our changes. Why is it not happy with map empty? It is happy with map empty. So this is a hash map. Let's help the type system here, or let's help future readers. And a step was a character sequence, a string basically. There we go. Types line up. We can get to work. We need to figure out the command in this step. So what do all the steps look like in our final example? It's sometimes more than 2 characters. So we need to take everything up until a minus or a equal sign. What's the cleanest way to do this? Some pattern matching? Yeah, let's do some pattern matching. Let's parse our instruction. So what can our instructions actually be? So it's a minus or an equals. Equals is put something in the relevant box, and a minus is take something out. Yeah, remove, and go into, so I'm gonna do add and remove. So let's do some more types. Remove of what? A label. I'm gonna type alias label. It's a string or a character sequence, but it's a string. So we can be clear and explicit. And this is a remove of a label or add of a label. So let's now write a quick parser that parses commands. It parses a step, so that's actually a step. Let's call it parse step. So I'm doing a pattern match here, but actually maybe not a pattern match. Yeah, we could use this pattern match, but let's keep it simple. So if we can do regular expressions, we can, but I'm not gonna. So if there's an equal sign in there, we can do split on equal sign. And that should contain the label and the focal length, right? And let's parse the focal length. So it takes the focal string, the raw focal, and it puts it into an integer. And now we can return add label, and we need the focal as well. So let's go all the way today with type aliases. Maybe not with wrapper types, but just type aliases. There we go. It's a bit more explicit. So we have label and focal length. And we need to put some, no? Yeah, okay, so it was just because we were missing an else branch. What do we do for our else branch? We can just assume it's a minus command, so we could do just a substring, or we can split on minus and it'll only be one element. That's symmetrical, I like that. So let's keep it like this. I think this will actually just work. Famous last words, and then we can say remove label. Okay, let's not be fancy and let's just annotate strings so our compiler is happy. Everything lines up. Okay, we took a big step by writing this parse step function. Let's see it in action. So parse step ABC equals 1, 2, 3. What does this give us? Oh, we're expecting an add, a labeled 1, 2, 3, ABC, yeah, and it should put in a length of focal length 1, 2, 3. That's correct, I think. And for the minus, it should parse in a remove ABC. Something like this. Match failure exception. Interesting. Match failure. Where are we even matching? Oh, it's one of these that's failing. So this is not working? What happens if I do ABC minus split on minus? Oh, it fills in an empty string for some reason. That's a shame. So maybe split was not as symmetrical as I would have liked. Or actually it is. Am I okay with this? It's confusing, but it's okay. So let's see if our tests now all run green. They do. Testing done. Okay, we can parse commands now. I don't like to do this in my fold actually. Let's first map our steps to commands by using a map. And then we don't need to parse them in here, and we can just say that these are steps. And now we can pattern match on step. So we did a messy parsing here. Now we can exhaustively match on things. And it's our add and remove cases. So it's add, label, focal length, or remove, and we'll figure that out in just a second. Okay, what needs to happen if we have an add instruction? We add or replace. Was it add or replace? If there's nothing in there, add it to the back of our box. If there is something in it with this value, replace. Cool. Add or replace. I'm just gonna write a helper function that helps me. I'm programming by wishful thinking. Something from the purple book. What's it called again? Structure SICP. Yeah, it's not purple. It used to be purple. But in this book, there's a lot of great stuff in there. But one of the things is called programming by wishful thinking, which is basically dreaming up your ideal functions as you need them and then implementing them. So that's what I'm doing. I wish I had this function, so I'm declaring it here, and I would provide it with the key. Oh yeah, what is the key? The key is actually hashing our step. It's not really what we're doing, so let's rename this function. Hash custom hash. What's our hash name? I'm just gonna say, of course, my resharper commands are not working for F#. So I'm just gonna do it like this. It's hash with 2 H's. That's our own hash. So I'm hashing the label to figure out the box number. And I want to add or replace our labeled lens. I'm not sure why I introduced that type. I'm not sure anymore, but okay. So this is the label. Focal length. Oh, actually, let's do it while we're parsing. So when we are parsing, we can build our labeled lens. Go away, please. Thank you. So that's our focal length, and we call that focal. And now this is a labeled lens. Slightly better, slightly better. So this is our labeled lens. And now it kind of makes sense to just try to add or replace our lens, I guess. And push all the hashing into our HASHMAP module. Makes sense. Let's make a HASHMAP module. So it's our wishful thinking function. It takes a lens and a map, and it returns a map. And it's in a module now, so we can prefix this function by the module name. And we can just say, okay, add or replace this lens in this HASHMAP. Reads pretty cleanly, so let's continue on. Lens is a labeled lens. Let's help the compiler so it can help us. And map is a HASHMAP. My auto formatting is not really working. Let me check that. What is it? F# tools formatting. I'm just using the built-in formatter. It uses Fantomas, one of the good old. Oh, it's not really doing a brilliant job actually. Oh no, what just happened? Let's see if I can Control Z my way out of this. Okay. I don't know what happened, but so I was saying the built-in F# formatting tool is actually pretty good nowadays, so we can just use that. I'm gonna fix my tests because I broke them by just changing the signature from underneath them. And if I do parse step right now, I get my labeled lens instead of a tuple. That's actually better, yeah. Okay, it's all good. Is my formatter working? Yes, it is. Cool. Okay, we're getting derailed here a bit. Let's focus again. We were working on our HASHMAP module and we were implementing our add or replace function. First, we need to figure out the key, which is hashing our label. Hash with 2 H's. And our lens has a label. So that's the key. And then we now our map contains lists of labeled lenses. Let's just wasn't there a map.update? Oh, there was a map.change. If it's not in there because our map is empty in the start, this change will do nothing. We provide a key and a function that takes an option, so it can... if it takes an option and it returns an option, we can do stuff, right? Let's play around with that. Let's take an empty map. I've not used that map.change function a lot before, so let's play around with it. Can I say map.change, the key 1, whatever, and we take something, an option, but it's not in there because our map is empty. And if I return sum2, does that work? Can we just like dream up? What the hell is this tuple? Returns a new map with the value stored under key changed according to F. Where is the tuple coming from? I'm super confused. Oh yeah, it's a key value, of course. Let's do it like this. So yeah, we can actually insert new values using map.change. I think I kind of like this function. It's a bit heavy on the types because there's options in there, but it works. I think we can, this will fit nicely with our problem. Map.change, cool, let's use it. So we have our key and we're going to change at key. And then we have a function that takes potentially the list of labeled lenses. And we return some new lenses, that's the idea. So I'm just gonna say lenses, yes. Or let's just write a new function. Let's wishful thinking. Let's program by wishful thinking again. So let's give it a function that, or let's make it very explicit. So these are lenses. It's an option, and it returns lenses an option. And this function we're gonna extract. So it takes the lenses and it's a pattern match on those lenses. If there's nothing in our map for this key, we say, okay, now there is something in there, namely our labeled lens. If there's already some lenses in there, we need to add or update in this list. And we can do that by saying lenses. Yeah, what's the best way to do this? So it can be that it's already in there, this label, and then we just update that one, we replace it. And if it's not in there, we plug in the new value at the end, right? Yeah, I'm just gonna write a recursive function. I don't know of a fancy way of doing it, but I think that'll just work. So it's like adding 3 ways deep. This is an add with a nested add, and now we're gonna write another add. This one works on maps. This one works on an optional list, and the next one works on the actual list. So I'm blanking on names. So forgive me, programming gods. So this is the function that actually works on lists. So yeah, let's say add to list. to make that a bit clearer. So this is a function we're going to call here. So add to list lenses and the lens, of course. So something like this. I don't know how to do it in a fancy way, so I'm just gonna write a recursive function, which says pattern match on lenses. If we are done, we did not find anything, we add the lens to the end. So if it's an empty list, it's a list with one element, namely the lens. Or when we have elements and h dot, I'm gonna call lens a labeled lens so the compiler can help us, or the type hint. Shouldn't it be able to figure out that h is a lens as well? No, I would have expected it to, but okay. It's a list of labeled lenses, people. So now I can say, there we go. If the first element in this list, or the element we're currently seeing, equals the labeled lens we have right now, then we replace h by lens and we work recursively. Tail recursion is not on the menu today. If we just replaced it, so that means we encountered it, we don't need to actually do anything recursively, we just plug in the tail again. So for now, no recursion necessary. Yeah, it'll be necessary in the next call. So, or in the next arm. Otherwise, so h does not match. Now we need to maintain h and do the recursive call, of course, add to list. Still the same lens we want to add, but let's continue on the tail end. There we go. We could rewrite this to be tail recursive. Don't suspect any performance problems for today's problem, so let's not do that just yet. So I think if we plug in this function here, type system is good and golden, and maybe we just implemented our add or replace. I took a huge step. Let's verify before we continue. So if all goes well, we can apply add steps. So if all goes well, we could play around with this. So let's actually try to work on an add step or two. rn is an add step, so let's grab that as an example. Let's parse that into a step and let's run that. And it doesn't work. So we're trying to add rn with a focal length of 1, and our code is saying, yeah, no, that's an empty map. That's a shame. So where's the bug? I think not a lot can go wrong, except in our add or replace. Let's try directly playing around with our add or replace. Now let's grab some random labeled lens. So let's try to add or replace this in an empty hash map. Yeah, so that's not really working very well. What's happening if we have an error place here, or if we have an empty map here? Sorry, we hash. Let me quickly alias. It's lens and map. So this is lens, and this is map. And now we can play around with this code as if we're calling it. So we can calculate our key. 198, sure, whatever. It has to be between 0 and 255. Whoa, this is working. What? Why is it working right now? Huh? Yeah, it's actually working. So is it working? Everything is okay. I did not send enough of my code to the REPL. So potentially add is working. Or at least for Rn is 1, for that step, it seems to work. We're adding to bucket 0 this labeled lens with the label Rn and focal length 1. That looks super correct. Cool. Do I want to see this in a test? Yes, I promised myself to take smaller steps. I'm just gonna do this entire thing in a single test case. So take these steps, parse them, do the thing, and I should have this map. That's not how you construct a map from a list. That's a map of sequence. That will work better. It's probably going to need some parentheses. Yeah, and then my auto formatter does stuff which I don't always agree with, but never fight your auto formatter. Okay, so that step works. We had one more command or one more type of steps, which was the remove. So let's implement remove in our apply step function. We are removing, what are we removing? Label. So let's write our remove. Oh, come on. My fingers are tired. So what do we do to remove? Let's take read again. So I think we kind of nailed our equal sign. Let's take a look at our dash. Go to the relevant box. So that means hashing again. Hashing the label, yes. And then remove the lens with the given label. Then move any remaining lenses as far forward as they go without changing order. That's just removing an element in that list, right? So that sounds doable. Parse step, no, apply step. That's where we are at. And we're writing our HASHMAP.remove function. So let's first find the key again. And then what happens if we try to remove something and we don't have a bucket? That's a no up, so yeah, a change will work here. So so this is an option of a list of labeled lenses, and if this is none, we do nothing. If it's something, we do something. So that's an option.bind. And what do we want to do? Again, do something with our lenses. No, what's the problem? We need to provide the key, of course. There we go. Then our bind has to return us an option, so it's not actually a bind, it's a map. Okay. That's some dense F# code. But if the compiler is not complaining, I think it's lining up. So what we're seeing here, we're using the same function, change key. This is a lambda that takes an option of lenses. If there's a value of key, we get some. If there's nothing, we get none. And this option.map does what you expect. If this is none, we do nothing. If it's some, we map whatever is in that option to whatever we do here. So in here, we can do our nested remove function, which we have not yet implemented. So it's a remove, what did we call it for our add to list? So let's write a remove from list. Let's keep it symmetrical. And we want to remove from a list of lenses a labeled lens. No, a label. and that returns the changed lenses. And then we can call that in here. Yeah, so we do lenses, remove from list, and we want to remove the label. There we go. I kind of like this playlist. It's the Streambeats Christmas playlist from Streambeats. It's free, it's usable without paying a dime, and it's quite catchy. Helped me get in Christmas spirits. But anyway, we were almost done. We are working on our remove from list function. Nothing happens if we don't find it, and otherwise we remove this one lens from the list of lenses. I'm just going to use an except. It's like a list difference, and you can provide a list of items to exclude. And that's just a list of one element, and I think that will work. Why is it not okay? Oh, it should be a labeled lens. Oh, yeah. So, yeah. So we need to do a list.filter. These are labeled lenses, and why is my compiler not helping, or my type inference? It should know that this is a labeled list. It knows it here. So it's a list of labeled lenses, sorry. So let's give this a type hint. So in the remove from list function, we take all the lenses and we keep the ones that are not labeled. And if it's labeled, we remove it. I think this might work. So let's give this a try. So let's add rn is 1. Keep qp3, qp minus. qp equals 3, qp minus should add something and remove something, right? So this should add something to box number 1. Yes, and qp minus should remove that from box 1 again. So let's verify that. Yeah, so the box is empty. It's now in our hash map, but that's actually exactly what I would expect. In the spirit of writing our tests, let's encode this in a unit test. So if we do this whole thing, that should be empty map, or a map with one element, namely box 1. Yeah, so it should be a label or box 1 with an empty list. That's what we expect. That's what you expect. So let's verify that. Yes, appears to work. It appears that all tests are still passing. So I think we are getting close. I think, can run all the different commands or all the different steps. Let's verify this for our example. Example is what? A string. Oh, sorry, I should take steps. Okay, we have something. 1, 3, 0. After OT equals 7, yeah, we should have a box 0 with RN1 CM2. CO2, yeah. 1 should be empty, that's right. 3 should contain OT, AB, and PC. That appears to be correct. Okay, so I think we have our algorithm down. Now let's calculate focusing powers and add them up so we can verify. I am having fun. This is a great puzzle. So yeah, let's continue. Focusing power, 1 plus the box number. Okay, so let's collect all our lenses with their box numbers and then we can calculate all these things. So let me just get this to the side, pull this in view. Okay, there we go. So this is the final hash map once we run all our steps. Now let's take all our lenses, which is HASHMAP. If we do a to list, we get tuples. Yeah, that's okay. And then we can map our tuples. And in our tuples, we have our box number and our labeled lenses. And now we can just say, okay, just take our labeled lenses, flat map or collect these, and smoosh the box and the lens together. So we have everything at the same level so we can start some lens power calculation. What's wrong here? Oh yeah, we're doing a flat map, but I don't know why we did that actually. This is where we need to do the flat map. So this lens is now a list of tuples, but I just want the flat list, so I can do collect instead of map, and now I have a list of tuples, which is exactly what we need, or exactly what I need to calculate the thing we need to calculate, I think. What was it again? We need to know the box ID, we have that. We need to know, oh, the slot. Yeah, so this won't work. We need to know the index. So let's get the index as well. Yeah, this will work. So we have the box, the index, and the lens. Cool. Box, index, lens. Box, index, lens. Yeah, so it's box plus 1. And what is this thing called? Focusing power. Let focusing powers equals lenses list map focusing power. So let's dream up a function that calculates what we need. And yeah, it takes a very massaged data structure, but that's okay. So yeah, let's put that in here. And that takes a tuple with a box number, an index in the box list, and a labeled lens. And it returns a numeric focusing power. And it's 1 plus box times the slot. So I'm going to call that slot instead of index. Is slot 0 based? First slot is 1, so it should be plus 1. So this is index, and if you do index plus 1, that's slot, and it's super unclear, but it will work, so that's good. And we have to multiply by the focal length as well, and that's in our lens, or in our labeled lens. And this is a lens. I'm just going to do focal length here, and I'm going to do focal length here. So this function is super context independent. It just takes a tuple of 3 numbers and does some magic. All the magic happens in this densely packed pipeline. But I guess it works. So actually, no, I'm going to leave it as is. This is not really a correct term. It's not the lenses. It's already the pre-massaged thing for focusing power. So not really happy, but I will not be bothered. Not when we're this close. And if we have focusing powers, 1, 4, 28, 40, 72, correct. We sum them. Whoa, what's happening? It's 145, it's 145. And for our input, it should be something else. Let's just do one more thing. Let's wrap another solve function around this. So this is the Altus for part 1. It can go. And we use input instead of example. And this should work for everything we throw at it. If we provide a type hint at least. There we go. So now we can write a test that verifies our example, and we can finish up for today. I forgot what it was already. My short-term memory is great. There we go, 145. Yeah, that rings a bell. That's correct. Our tests are green, so let's run on the input. We have a number, pretty confident. With good reason, that's our second start down. Ooh, and in 10 hours we have the next one coming up. Yeah, but let's first recap day 15, lens library. Let's first dive into part 1 and then take a look at part 2. Part 1 was basic. We just had to split our input into steps and then run the hashing algorithm on the entire step. Hashing algorithm was pretty straightforward, and because we could, we just used a fold. I am a big fan of folds, as you can see if you watch the entire series. Meta comments, I started doing a bit more of this. I'm trying to hold myself to do that more. But part 1 was pretty basic, as you can see. It was 20 lines of code or 10 lines of code, even in a language like F#. And then for part 2, things got a bit more interesting, but not much. But we did some interesting things. We did some type-driven development, where we took a look at the types first, and then wrote functions that worked on these types. So we could find misalignments or mismatching input-output types better. And I mean, the compiler can help us a lot as well if we provide these type hints. Another cool thing we did was this module thing. So if you have a type and you have functions that kind of belong to the type, in C# or OO languages, you would put on methods on objects or on classes. In F# you can define modules and types that like belong together, so you can find corresponding functions or functions that work on a type. You can find them more easily. And this is one way of doing it. It's not the only way. So we defined our add or replace and our remove. We kind of defined our own hash map, but we used the HASHMAP, a backing HASHMAP as well. And today I found out, or I think we used it before, but I really got to play around with map.change, which was a new function for me this year. I don't know how old it is actually, but I've never seen it before, so I'm thinking it's more recent. And there we noticed that we had to do some work with options. Here we do an explicit pattern match, and somewhere else we did option.map. So that's not really symmetrical. That's not my favorite way of doing things. Yeah, here we did an option.map. So we could actually make these two things more symmetrical, but now we've seen both. So now we know how to do both. And if we had our HashMap add and remove functions, we also did some parsing, so we knew whether or not it was an add or remove step. I still suck at regexes, so it's back to string splitting and if statements here, but it works. Or it kind of worked once we figured out this one. Apply step is a basic pattern match, and calling the right functions, and focusing power was just a basic calculation. So yeah, I had fun today. It was a not too thinky, just go and program kind of problem, and I needed that after this week. So thank you very much, Advent of Code. That's it for today. I hope you enjoyed your time here with me, and I hope to see you again for more Advent of Code in F#. Bye bye.